The present problem simulates the external airflow on the body of a car using ANSYS Fluent software. The three-dimensional geometry of this model is designed using Design Modeler software. Also, the meshing of the model has been done using ANSYS meshing software. The simulation is steady. From the mesh display section, we can display every surfaces of the computational domain, including inlets, outlets, walls, symmetries, and so on. We can check all the materials properties in this section. The car wall is a stationary wall with no slip. The velocity inlet boundary condition has been specified for the inlet surface, and also the velocity magnitude is equal to almost 77 meters per second. And all the other lateral walls and sides are assumed to be as a symmetry in the boundary condition section. The pressure implicit with a splitting of operators or piezo pressure velocity coupling scheme, part of the simple family of algorithm, is based on the higher degree of the approximate relation between the corrections for pressure and velocity. One of the limitations of the simple and simple C algorithms is that new velocities and corresponding fluxes do not satisfy the momentum balance after the pressure correction equation is solved. As a result, the calculation must be repeated until the balance is satisfied. To improve the efficiency of this calculation, the piezo algorithm performs two additional corrections: neighbor correction and skewness correction. For setting under relaxation factors, we should say that the pressure-based solver uses under relaxation of equations to control the update of computed variables at each iteration. In ANSYS Fluent, the default under relaxation parameters for all variables are set to values that are near optimal for the largest possible number of cases. These values are suitable for many problems, but for some particularly nonlinear problems, for example, some turbulent flows or high Rayleigh number, natural convection problems, it is prudent to reduce the under relaxation factors initially. It is good practice to begin calculation using the default under relaxation factors. If the residuals continue to increase after the first 4 or 5 iterations, you should reduce the under relaxation factors. Occasionally, you may make changes in the under relaxation factors and resume your calculation, only to find that the residuals begin to increase. This often results from increasing the under relaxation factors too much. A cautious approach is to save a data file before making any change to the under relaxation factors, and to give the solution algorithm a few iterations to adjust to the new parameters. Typically, an increase in the under relaxation factors bring about a slight increase in the residuals, but these increases usually disappear as the solution progresses. If the residuals jumped by a few orders of magnitudes, you should consider halting the calculation and returning to the last good data file saved. This is the pressure contour, and as it is obvious, the maximum pressure occurs when the wind flow collides with the car body at the front of the car. The graph of drag and lift coefficients in terms of the number of the iteration are obtained. A summary of the defining steps of the problem and its solution is given in the following tables as a review. Obtain the mesh file and also the full training movie by purchasing this product. A rectangular cube area is considered as the computational domain of the open airflow in which the wind enters this computational area horizontally. This wind flow hits the front of the car directly and creates aerodynamic forces on the car. The three-dimensional geometry of this model is designed using Design Modeler software. The present model includes a rectangular cube computational domain with for the airflow in which a car is located. Also, the meshing of the model has been done using ANSYS meshing software, and the mesh type is unstructured. Also, the meshing accuracy is higher at the vicinity of the car surface. To benefit from Master CFD services, including simulation, consultation, and training, contact our experts via info@mastercfd.com.